Makaku once commented that we will require to rework our course readings on the start of the universe. Everybody has been enthusiastically anticipating a specific picture, which has now been made public. This picture from the James Webb Telescope uncovers uncommon cycles in the universe that challenge our logical understanding. Since the send-off of the telescope, not only have our speculations on the universe's starting points been tried, but indeed, even exoplanets have begun to oppose our comprehension of material science, totally flipping around our thoughts. What new circumstances and answers can researchers find in light of these incitements? We are now seeing a total commotion of the old principles in science. The James Webb Telescope is changing our impression of the universe, and each new picture from this wonder of room investigation is momentous. James Webb, the telescope's namesake, would have been glad. Webb was not a researcher but rather came from a business foundation. He comprehended the significance of space investigation for humankind as head of NASA during the 1960s. Webb advanced space travel, essentially sending off the Apollo program and upholding for space tests. Today, researchers are surprised by the abilities of the telescope named after this trailblazer. The pictures are so clear and sharp that they take our breath away. Interestingly, we have complete examinations of exoplanets some large number of light-years away. The telescope is uncovering to our logical community that they have been depending on obsolete discoveries and thoughts for a really long time. At first, numerous researchers are encountering vulnerability and inconvenience, as all that they had faith in may now be refuted. Mio Kaku, a famous astrophysicist from the USA, is one specialist who is hopeful about these new improvements. Kaku has long contended that our past hypotheses were inadequate. The powerlessness to join the universe of subatomic particles with the universe of framed matter alone demonstrates that we have not completely understood central cycles in the universe. Presently, exoplanets are likewise breaking the laws of material science. It's shocking. At first, only old cosmic systems didn't squeeze into our cosmological models. Then, at that point, came dark openings and tremendous designs over 13 billion years old, when the universe was probably in its earliest stages. Presently, even planets oppose our past understanding. The most recent pictures from the James Webb Telescope show exoplanets that challenge our past thoughts regarding planetary data. The telescope reevaluates probably the most abnormal known exoplanets with its sharp eye and extraordinary exhibit of spectrometers. The instruments can separate even the slightest light signals into their singular parts, investigating hints of components, gases, proof of water, and boundaries that uncover the size and circles of far-off planets. In the process, Webb views as more oddities, limits, and the most insane planets. One wonderful illustration of these incomprehensible universes that challenge the very essence of material science is K2-9b. An ultra-hot Neptune circling so near its star that its surface temperatures are high enough to part water atoms into nuclear hydrogen. The outrageous nearness to its star prompts a peculiarity researchers called air blow-off, where the planet's atmosphere is in a real sense blown away from the star. This revelation is novel among all known planetary climates and presents a critical test. Webb sees as so many exemptions and limits that it's genuinely incomprehensible. K2-9b is bizarre to such an extent that it's nearly difficult to characterize and addresses a total exemption for every one of the guidelines we've laid out. How about we think about a different universe that frightens researchers? WASP-76b, a Goliath exoplanet with iron pouring from the sky on its night side. The planet circles its star in a neatly locked circle, resulting in very hot and chilly sides. Metals liquefy and disintegrate on the hot day side, cementing into iron on the far side, then tumble to the ground like rain. Indeed, researchers are managing outrageous conditions that stunningly illustrate the actual cycles on exoplanets and raise additional questions than answers. Especially interesting and perplexing is the revelation of planets circling their stars the other way to other planets in the same framework. Such discoveries compel cosmologists to reconsider hypotheses about the elements of planetary frameworks and the powers that decide their circles. WASP 717b is an illustration of such a world. This exoplanet, found as part of the wide-angle search for planets, is a tremendous gas monster resembling our Jupiter. However, it circles its star in a retrograde heading, opposite to the star's revolution. This was thought of as deductively unimaginable, according to current speculations of planetary development, which suggest all planets in a framework ought to circle in the same heading as they formed from the original protoplanetary plate. One hypothesis that makes sense of such circles is that gravitational annoyances from nearby passing stars or other huge planets can emphatically change a planet's circle after its development. Another possibility is that a gravitational dance between a few enormous planets can push one or more into a retrograde circle. Curiously, we don't need to look past our nearby planet group to find peculiar planets. In the Kuiper belt, we find the dwarf planet 2018 VG18, which surveys have demonstrated to be curiously dim and red. Webb spectrometers uncover that this planet is possibly rich in complex natural mixtures, which researchers call tholins. Notwithstanding its significant size and idiosyncrasy, 2018 VG18 remains without an official name since its precise circle is yet to be decided. Its plausible structure, rich in natural substances that are the building blocks of life, and strange variety don't match other dwarf planets in the Kuiper belt. This raises questions. Where does this planet come from? How did it form? And why is it so hard to see? Because of its huge span, noticing 2018 VG18 precisely and over a significant stretch is very difficult. Indeed, even with our best telescopes, it is potentially the third largest dwarf planet after Pluto and Eris, and analysts see it as a vital item for understanding dynamic cycles in the Kuiper belt and the advancement of the planetary group. Drifter planets without a star. Is that conceivable? Would you trust there are planets without a star? Planets normally form in the residue and gas plates left over from star development, remaining gravitationally bound to their star. Anyway, drifter planets show that this isn't generally the case. These inestimable introverts float unreservedly through space without a star. However, where do they come from, and how might they get by in the antagonistic cold of room? Drifter planets can form in different ways. One common technique is launch from their unique star framework because of dynamic connections with different planets or close stellar flybys, with gravitational powers sufficient to haul the planets out of orbit. Another possibility is that they formed as detached objects in a star-forming area, yet without sufficient mass to start atomic combination processes like stars. This could likewise make sense of the presence of items called jumbos, which are Jupiter mass-like items that didn't acquire sufficient mass to start atomic combination and become stars. Jupiter, the largest planet in our planetary group, was barely short of the mass expected to start these cycles. The James Webb Telescope stunned the academic community again when it found 80 such drifter Jupiter mass planets in the Orion cloud. The odd part of this disclosure is the nearly staggering truth that these 80 planets have formed 40 double frameworks, meaning 40 sets of drifter planets circle each other inside the somewhat restricted space of the Orion cloud. This is odd and deductively unrealistic. The sheer number of these planets might be due to the Orion cloud being one of the most extreme star-forming areas known. Anyway, more detailed investigations showed that these items are not really planets but somewhere between planets and earthy-colored diminutive people in terms of mass. This proposes they are failed stars, as brown dwarfs are among the littlest stars known. However, what processes in the Orion cloud are responsible for these fizzled stars that behave like planets, unreservedly moving through the universe in binary frameworks? This is another limit challenge for our researchers. These objects probably form their own class, pushing the limits of our astronomy. It is conceivable that such gigantic free-floating items are a lot more normal in the universe than we figured they might be. Ordinary yet strange to us since we were beforehand ignorant of their reality. We have not had the option to identify exoplanets in the profundities of room for an extremely long time, and concentrating on them has forever been testing. The James Webb Space Telescope addresses an achievement in this regard. We are excited by these revelations, yet science researchers are becoming overwhelmed by the new peculiarities and unthinkable discoveries. Nothing is as they expected. Has science arrived at an end? The James Webb Telescope was made to fill gaps in our information and affirm existing hypotheses. Rather than shutting gaps, its discoveries are tearing new openings in what we consider insights. Some now say that the emergency web has set off marks the finish of our old science. As Mio Kaku said, we will require to rework our course books. But what ought we to write in them now? No sound new answers have yet been found, and analysts are frantically looking for new clarifications. Dissimilar to its ancestor, the Hubble Space Telescope, which fundamentally sees in the noticeable and bright frequencies, JWST is upgraded for infrared perceptions. This ability permits it to look through grandiose residue mists, concentrate on the arrangement of stars and worlds, and even portray the environments of far-off exoplanets. One of the essential logical objectives of JWST is to unwind the mysteries encompassing the starting points of the universe. By contemplating the light from the most far-off universes, the telescope can give bits of knowledge into the beginning phases of inestimable development, not long after the enormous detonation. This incorporates the cosmos and our place within it. As we venture further into the depths of space exploration, it becomes increasingly clear that each discovery not only adds to our knowledge, but also opens new avenues for inquiry and understanding. The revelations brought forth by the James Webb Space Telescope, JWST, and ongoing missions like Explorer-1 challenge us to reconsider our understanding of the universe. The implications of these discoveries extend far beyond our immediate knowledge of distant galaxies and exoplanets. They prompt us to explore fundamental questions about the nature of existence, the formation of celestial bodies, and the very fabric of reality. As we encounter these anomalies, planets with unexpected characteristics, exoplanets with bizarre atmospheres, and even the potential for rogue planets floating through the cosmos, we are faced with the possibility that our current models of astrophysics may need substantial revision. Moreover, the collaboration between different space agencies and scientific communities plays a crucial role in unraveling these mysteries. The exchange of data, ideas, and resources enriches our understanding and enables researchers worldwide to work together toward a common goal: uncovering the truths of our universe. This spirit of collaboration is essential, especially as we confront the challenges posed by new findings that defy our established theories. The JWST, equipped with its state-of-the-art technology, is not merely an observational tool but a revolutionary instrument that allows scientists to push the boundaries of our understanding. Its ability to capture high-resolution images of distant celestial objects enables researchers to analyze their properties in unprecedented detail. As we gather more data from the telescope, the scientific community is tasked with synthesizing this information to develop coherent theories that explain these extraordinary observations. As we stand on the precipice of a new era in astronomy, it is essential to recognize that the pursuit of knowledge is inherently iterative. Each discovery leads to more questions than answers, fostering a cycle of exploration and inquiry that is fundamental to the scientific process. The anomalies observed in our universe are not just obstacles. They are invitations to rethink and refine our models of reality. Looking ahead, future missions and advancements in technology will continue to shape our understanding of the universe. The search for habitable exoplanets, the study of cosmic phenomena, and the quest to understand dark matter and dark energy remain at the forefront of astronomical research. Each new mission will build upon the findings of the JWST and other telescopes, gradually painting a more comprehensive picture of the cosmos. In conclusion, the discoveries facilitated by the James Webb Space Telescope and the challenges posed by recent findings serve as a reminder of the vastness and complexity of the universe. As we continue to explore and investigate, we must remain open to new ideas, embrace the uncertainties, and recognize that our understanding of the cosmos is ever evolving. The journey of discovery is far from over, and as we advance, we may find that the universe holds even more surprises in store for us.